Hello, welcome to the another session of Turbo Machine. Today we will be dealing with another problem. Let us read the problem once. 4 turbines of specific speed 890 metric. So in the earlier classes we have already discussed what is specific speed of a turbine, what is specific speed of a pump. In the specific speed of a turbine, power is the most significant thing. In the same way, for a pump, the business end of the pump is flow rate, that is Q. For a turbine, it is power. So this is the difference between specific speed of a pump and turbine. Since it is a problem of turbine, here the power factor should be there, or the power component should be there in specific speed equation. And another thing is specific speed 890 metric. So the specific speed can be expressed in two ways. One is in SI units and another is in metric units. So in this problem, specific speed has been expressed in terms of metric units. So there are 4 turbines and the specific speed is 890 metric. Each is installed in a hydral station. Okay. So it is a hydraulic power plant. Okay. Full stop. Each of the turbine runs at 50 RPM. So there are 4 turbines. You can see here 1, 2, 3, 4. Each of the turbine is running at the same RPM, that is 50. Shares equal of total discharge of 260 meter cube per second. So we can see that from the reservoir, the total flow rate which is going to all of the turbines is 260 meter cube per second. Available under a head of 1.73 meter. So what is the available head for the turbine is, we can see from the inlet of the turbine to the upper level of the reservoir, it is total of 1.73 meters. Full stop. Assuming each turbine has a efficiency of 82.5. So all the turbines are having equal efficiency and also is having equal or running in equal speed, sharing a equal amount of flow rate for each of the turbine. Okay. So I have just tried to picturize the problem in terms of a pictorial format. You can see a reservoir here which is feeding the water to the turbines. So here is the main pipe where QT amount of flow rate is happening, which is 260 meter cube per second. Once after this, the flow rate is going to equally distribute for all of the turbines. We need to calculate how much it is, and each of the turbine is running at a same speed of 50 RPM, and the head available for each of the turbine is 1.73 meters. Now what is the thing to be found in this problem is, find the power of each turbine in kilowatts. So let us start with the problem. So first we need to write the data. So we know that there are 4 turbines. So N I have written it as 4. Next, specific speed. Specific speed is always expressed for one individual turbine. So you cannot say the specific speed as to the all the 4 or total number of turbines inclusive of all. Specific speed cannot be said. Specific speed is always mentioned for one particular turbine at a time. So and all the turbines, all the 4 turbines are having the same specific speed in this particular problem. So next is speed of each turbine. So that is 50 RPM. Next, head available for all the turbines, it is common, so it is 1.73. Next, the efficiency of all the turbine are also same. So this is a ideal problem. So in case of actuality or in reality, things will vary from one another. That means all the 4 will vary with slight amount of efficiency, RPM and so and so. Since it is an ideal problem, the author has given in such a way that all the turbines are having the same parameters. Next, the total discharge, that is Q suffix T, it represents total, it is 260 meter cube per second. We should be knowing that 260 meter cube, it is not a small volume. 1 meter cube means 1000 liters. 1 meter cube per second means in a pipe section 1000 liters of water is crossing the section in a unit time of 1 second. 1000 liters, it is not a small thing. Here it is 260 meter cube per second. 260 meter cube means, if I express in terms of liters, it becomes 2,60,000 liters per second of water flow rate in total is going to the turbines of all the 4 turbines. Now, how much amount of discharge is being shared by every individual turbine? This we have got by dividing by 4 by Qt, Qt by 4. So, we will get 65 meter cube per second. So, this is the amount of flow rate of water which is going through each of the turbine. Now, we know that specific speed of a turbine, that is represented by the notation Ns is equal to N into under root P divided by H 5 by 4. So, N is RPM, P is power produced by every turbine, individual turbine. P, as Ns is in metric, we have already discussed in the previous class that P should be in metric horsepower. If Ns is in SI units, the power P will be in terms of kilowatts. In this problem, since Ns is in metric terms, the power which comes out of this problem will be in terms of metric horsepower. We should be very careful about this. Next, head is, H is head in terms of meters, N is in terms of RPM. So, we have substituted the given data here, that is 890 metric. So, in place of N it is 50 RPM, P we do not know, we need to find it. Next head is 1.73. So, after solving this equation, so I will get, this is the ideal power or theoretical power. So, of each turbine I am getting 1247 metric horsepower. This is of individual turbine. Next, to find the actual power produced by each turbine, since this is the ideal power, so obviously there will be certain amount of losses. To find the actual power, what are we doing? We know the efficiency formula. The efficiency is equal to P actual by P ideal. So, rearranging it to find the P actual, I have just multiplied P into efficiency. So, further doing it, the actual power output by each of the turbine is 1028 metric horsepower. Now, to convert this metric horsepower into kilowatt, I have just multiplied 0.736. What does 0.736? It is a conversion factor, or I can also say that 1 kilowatt is equal to, 1 horsepower is equal to 0.736 kilowatt. 1 horsepower is equal to 0.736 kilowatt. So, for that reason, I have just multiplied 0.736 to metric horsepower, so that I will get it in terms of kilowatts. Next, this is what is the solution or the question asked by the author. So, the power produced by each of the turbines in terms of kilowatt. This is the solution. So we are going one step ahead to see that what is the total power output by combination of all the 4 turbines. That is just the actual power you multiply with the number of turbines, which is 4 in this particular problem. So we are getting 3028 kilowatt. This is the total power produced by this entire hydro power plant. Going on to the next problem. First, reading the problem, the quantity of water available for a hydro station is 310 cumses. Here cumses is a other name given instead of meter cube per second. So you need not to get worried just because looking into cumses. It is just an alternate name for meter cube per second. It is, you can see here, cubic meter second. Okay. Next, under a head of 1.8 meter. Full stop. Assuming speed of each turbine is 60 rpm and efficiency of 85%. Full stop. Find the number of turbines required and power produced by each turbine. Full stop. Each turbine has a specific speed of 800 metric. So going through the problem, we can understand that the total available flow of water is 310 meter cube per second. The next thing is the head available. Here I have written in a pictorial format. The head available is 1.8 meter. Next, speed of the individual turbine is 660 rpm. Next, overall efficiency is 0.85 and specific speed of each turbine is 800 metric. Now, what has been asked in the question is find the number of turbines required and power produced by each turbine. So we are supposed to find the total number of turbines which is required to find the total power output. So we have been given the data also to find total power, that is the power output combining of all the turbines, and also sufficient data has been given to also find the individual power output of each turbine. Now we can take anything for as a first thing. So here I have taken the scenario to find the total power output as the first calculation step, or else you can also take to find the power output of individual turbine also. It is up to the individual requirement, or it can be done in both the ways. So first, to find the total power which is being output from this hydro station, so I have written the efficiency formula. The efficiency formula is the actual total power output divided by the theoretical total power input to the entire hydro station. This is the theoretical power input to the entire hydro station. This is the actual power output inclusive of all the turbines from a hydro station. So here the overall efficiency has been given. The density of water, it should be known, that is 1000. Discharge has been given. This Q is total discharge, that is I will write it as QT. That means to say, if the Q which I have represented in the figure, here I have just written one turbine. Here the amount of flow to one individual turbine, that is just Q, which is the flow rate to the individual turbine, is not known. And in this particular problem, it is also not necessary to find the individual flow rate. Without finding this, we will be directly going to we will be finding the solution. So this QT is the total flow rate inclusive of all the turbines. G is gravity constant and head is available head. Next, so once I write down this formula, the only unknown thing is the total power. Rest of the things has been given as a data, and some of them are constants. Now total power, just I have rearranged this equation. Total power, I will be getting it in terms of metric horsepower. The reason is, so the power what we will be extracting, we will be extracting so that I will be getting it in terms of metric horsepower. Why? Because when I am finding the power of the individual turbine by using this formula, I will get the power in terms of metric horsepower only. So also the total, while I am calculating the total power, I should make sure I am finding the total power in metric horsepower. If to get it in metric horsepower, I just need to do or divide it by 736, so that it automatically gets converted into metric horsepower. If you don't divide this equation by 736, you will directly get it in terms of watts. So this total power in terms of watts and individual power in terms of metric horsepower, there will be no unit consistency. So we will be surely ending up with a wrong answer. So it should be always taken care that while multiplying or dividing or adding or subtracting, there should be unit consistency. So for that reason, I have converted this total power in terms of metric horsepower. So after doing it, after solving this equation, I am getting 6321 metric horsepower. This is the total power output of this hydro station. Next, we will be trying to find the power output of individual turbine. So we can get the power output of the individual turbine by making use of specific speed equation for a turbine. So I have written the specific speed equation. So here the specific speed has been given in terms of metric. So once ns is in metric, P also comes out in metric. That means the power unit in metric is metric horsepower. Okay. So I have substituted 800, which is given in the data. 60 is the RPM of individual turbine, and 1.8 meters is the available head. After solving this, the power produced by the individual turbine has been got as 772.8 metric horsepower. So now we know the total amount of power produced by all the turbines divided by power produced by individual turbine. By doing this, I will get to know the number of turbines which is required, which is coming out to be as 8.2. So as all of us know that partial turbine cannot exist. So what we are doing is, we are stepping up into the higher number, so it becomes 9. So if you install totally 9 turbines, so we will be fulfilling the amount of, or that will be, the 9 turbines will be consuming 310 cumes of water under a head of 1.8 meter, which will be producing 6321.85 metric horsepower. At the individual level, when it is rotating at 60 rpm, it will be producing 772.8 metric horsepower. Thank you. Moving on to the next problem. So this is a problem about model and prototype. Let us first understand what is the meaning of model and prototype. Suppose if there is a dam to be constructed, or a ship to be built, or an aeroplane to be assembled, any of these machines we cannot directly construct it and then leave it for working, or you cannot put it into application. Why? Because they are very huge, they require hundreds of crores. So we cannot invest such a huge amount directly constructing, and if something goes wrong, it cannot be corrected that easily. For the same reason, usually the technique of engineering is to produce a very miniature or small scale models, as for example dams, bridges, or it might be for aeroplanes, ships. After doing the model type, all the kinds of analysis will be done on it, and if there is anything to be corrected, it can be very easily corrected when it is in a model type. The model type will be of a very small structure which could be analyzed very easily and also can be corrected. So always for mega structures, model type will be done first, and then it will be next implemented to the prototype or to the actual one itself. So this problem is of that kind. So we have model and prototype which is to be solved. So just pictorially representing, I have written this machine as a model type, and the another one is representing the prototype. The model I have represented small. Usually it will be small than compared to the prototype, need not to be always. Okay. Under that I have written all these model and prototype are geometrically similar machines. Geometrically similar means only the scale size will be different, the entire geometrical structure will be similar to each other. So there will be no change in geometry or proportions, but there will be a massive or huge amount of change in scale or size. So once we know that the model and prototype are always of geometric similarities, so geometrical similar machines will be having the same flow coefficient, head coefficient and power coefficient. Even though the machines are different, they are similar to each other. So the coefficients such as flow coefficient, head coefficient and power coefficient of geometrically similar machines will always remain same, it will not vary. So by making use of this particular point, we will be solving this problem, and also I have written this as a note. Okay. So first I will write down the data, so that for that reason I should read out the problem once. From the performance curves of turbines, it is seen that a turbine of 1 meter diameter acting under a head of 1 meter develops a speed of 25 rpm. So there is a miniature version where the turbine is having a diameter of 1 meter and is acting under a head of 1 meter, which is running under a speed of 25 rpm. What diameter should be the prototype have if it develops 10,000 kilowatt working under a head of 200 meter? So we can understand in this sentence the information whatever has been given is related to prototype, and the first sentence information is related to the model type. So next is with a specific speed of 150 SI unit. This specific speed doesn't belongs to model or to prototype. It is same for both model and prototype. This is a common information. Okay, let us first write down the data of the model. So for the model, the diameter of the model's machine is 1 meter and the head available for this model type is 1 meter, and the speed at which the model turbine is running is 25 rpm. Similarly, for the prototype, the power output of the prototype is 10,000 kilowatt, the head available is 200 meters, the diameter of the prototype yet to be found. This is the solution to be found in this problem. Next is specific speed. It is not of model, it doesn't belongs to either model or prototype, it is a common information. So I have not mentioned, it is just specific speed. You are not supposed to write this as specific speed of a model or specific speed of a prototype. If you do so, it becomes wrong. It loses its meaning. Since both are geometrically similar, the specific speed is same or common for both of these machines. Next is the specific speed. I am here about to find. So the value of the speed of the prototype, that is the RPM of the prototype. So here P means prototype, the speed of the prototype machine, the power of the prototype, the head of the prototype. But here I have not mentioned specific speed of prototype. Why? Because it is same. Okay. So after substituting this, I am getting the RPM of the prototype is 1128 RPM. What is the RPM of the model type? We have already written in the data, it was just 25 RPM. The specific speed of model and prototype will be same, this we know, but the RPM or the speed of the prototype and model will not be same. The same things will be the flow coefficient, the head coefficient, the power coefficient. The same way, the specific speed of geometrically similar machines will be same. The specific speed will be same, not the speed. This should be noted. So that is why we can see that the speed of the prototype is 1128, whereas the speed of the model is just 25 RPM. So you shouldn't get confused between the speed and the specific speed. Okay. Next, once I know the speed of the prototype, by making use of the head coefficient, if possible we can also make use of power coefficient or flow coefficient, whichever feasible to be used out of these three coefficients, that we will be choosing here. There is no mandate that I should be using only head coefficient, whichever is feasible, that we will be choosing of these three coefficients, that is flow, head and power coefficients. Now for this particular situation, I am choosing head coefficient. Why? Because most of all the terms is known or given in the data. So I am just writing the head coefficient of the model is equivalent to the head coefficient of the prototype, since both are geometrically similar machines. So I have written head coefficient for the model. You can see that the suffix has been put for head, speed and diameter, whereas for G I am not writing suffix as M. The reason is G is the constant, it doesn't belongs to model or prototype. So while writing the denotions, we should be very careful. In a similar fashion, on the right hand side, where I have written the head coefficient for the prototype, so I have exempted G, that is head of the prototype, speed of the prototype and diameter of the prototype. Solving this, the only unknown thing is diameter of the prototype. So rest of all the terms, that is head of the model, head of the prototype, speed of the model, diameter of the model, everything else is known. So the only unknown thing is dia of the prototype. So this comes out to be 0.098 meter. So this is meter square, since it is dp square. Next, after taking off the square, so I will be just left with the diameter. So this will be the dia of prototype. So this is still in terms of square. So this is the answer we are supposed to find. That is what has been asked, what diameter should be the prototype have if it develops 10,000 kilowatts. To produce a power of 10,000 kilowatts, the prototype's diameter should be 0.313 meter. So this is the solution for this problem. Thank you.